All right, this is really exciting. Up until now, we've been doing basically half of calculus. We've been working with derivatives and applications of derivatives. We're going to start next. This section is introducing or talking about integrals, which is really the antiderivative, is going backwards. But just to introduce this, I want you to take just a second, look at these three examples and take the derivatives. So pause the video, take the derivatives, and then come back and we'll talk about them together. All right, so on this first one, right, when I take the derivative, 3 drops down, subtract 1 from the power, so my derivative is 3x squared. On the second one, same thing, 3 drops down, subtract 1 from the power. It has the minus 10 on the end, but that's a constant, so it comes out to be 0. So we get the same derivative. We get 3x squared. Take the derivative here. 3x squared, it says c is a constant. Well, the derivative of a constant is 0, so you get the same thing. So the point we're trying to make here is that it doesn't matter if you have a constant on the end when you take a derivative, because the constant's going to go away. Well, that's important because, like I just talked about, we're going to be finding the antiderivative or the integral. So if you look at this, I want to find the antiderivative of f prime of x is 3x squared. So if I want to find out what f of x would equal. Well, we just did that, right? If the derivative is 3x squared, I know the original function would have to be x cubed, right? So the 3 would drop down, subtract 1 from the power, would get the 3x squared. Now the issue is here is there could be any number on the end. There could be a constant on the end, and we don't know what it is. So what we do to take care of that is we just put a plus c right there. And that c represents some constant that I don't know. When you go to find the antiderivative, another way of writing that, instead of having to write out, find the antiderivative of f prime of x equals 3x squared, instead we can use what's called an integral symbol. It's this little symbol right here. So it looks kind of like, almost like an S. Okay, and all that means is take the integral of 3x squared. The dx tells you that you're taking the integral with respect to your integrating with respect to x. You don't do anything with it, so it doesn't affect at all what your answer is going to be. It's just always going to be the hook-on thing right there that tells you you're taking the derivative with respect to x. So there's a couple of vocabulary things. I think we've talked about most of this, right? But this is called the integral symbol right there. It tells you to integrate or find the antiderivative. The expression is called the integrand, so the whole thing is called the integrand. The dx indicates that you are integrating with respect to the variable of x, but does not. This is really important if you want to underline that. It does not affect the integration process. So all it's doing is telling you that you're integrating with respect to x. That's it. Then we're always going to put that plus c on the end. That plus c is called the constant of integration. It has to be written as part of your answer when you're integrating, when you're antidifferentiating. And the reason why, again, is because there is some constant we don't know on the end. When you take the derivative, it's going to go away. So when we integrate it, we know there's something there. We just don't know what it is. So we have that plus c there. By the way, that's required on the AP test. So that's not something you want to lose points for, is not having a plus c. So we'll try to get in the habit of adding that whenever we integrate. So I want you to think for a second. We just took the derivative of x cubed. Right? When I take d dx of x cubed, our power rule is the 3 drops down in front, you multiply by 3, and then you subtract 1 from the power. So if we're integrating, we're going to work backwards. So what we're going to do is, if you think of the inverse, think of inverse operations. So first I times by the 3, then I subtracted the exponent. So when I work backwards, I'm first going to add 1 to the exponent. So I add 1 to the 2 and make it x cubed. And then I divide by what that new power is. All right, and that takes me back up to the x cubed. So that brings us to our first rule of integration, which is the power rule. So just think we're working backwards. Instead of dropping the power down and subtracting 1 from the power, we add 1 to the power, and we divide by that new power. Okay, so that's our product rule right there. Constant rule, just again, if I take the derivative of, say, for example, 5x, that is just equal to 5. Well, then if I integrate 5, if I'm going backwards, I find the antiderivative of 5, it's just going to be 5x. So if k is a constant, if I integrate a constant, I just add an x on there, kx plus c. Okay, just go in the opposite direction. Scalar multiple, if you have k times any function of x, k is a constant. and we're just multiplying by a constant, we can move that on, we can factor that out or move it to the outside of the integral. We can just ignore it. I can find the integral of f of x, find my answer, and then multiply it by k afterwards. So constants can be factored out. This is, if you want to think of it that way, is factoring it out of the integral expression. This is really important. You can never factor out a variable. So if you have x times f of x, you can't take the x out in front. But if you have 5 times f of x, you can move the 5 out in front. The last one is a sum rule, and this is just like, I think this is pretty common sense because we already know this with derivatives. If you take the derivative and you have functions added together, f of x plus g of x, we talked about how you can just do them separately. I can take the derivative of f of x and take the derivative of g of x. Well, same thing holds true of integrals. If I have the integral of f of x plus g of x, I can separate it and take the integral of f of x plus the integral of g of x and just do it really term by term. Let's do some examples here. So I'd want to take the integral of x cubed dx. So be careful, this is not derivative now, this is the integral, so we're working backwards. So I add 1 to the power, so x to the 3 plus 1, then I divide by whatever that power is. Right, so really that's going to be x to the 4th divided by 4. And then don't forget the plus c. All right, 5, I have 2 dx. Well, 2 is a constant, so if I integrate it, all I do is just add an x. Make sure you don't forget the plus c. So the integral of 2 equals 2x plus c. And if you're not sure, just check the derivative, right? On this first one, if I take the derivative, the 4 would drop down. It'd be 4, subtract 1 from the power. Those would cancel out. That gives me the x cubed, and the derivative of c is just 0, so it goes away, right? So I end up with the x cubed that I started with. All right, the derivative of 2x is 2. Derivative of c is 0, so I end up with 2. All right, so number 6, I can separate those. The integral of t to the 4th dt plus the integral of 2 dt. That's using that last rule that we talked about. Can integrate each one, so t to the 4th would be t to the, add 1 to the power and divide by that new power. Integrate the 2, be 2t, and then the plus c. We don't have to put the plus c twice. If I did put it twice, let's go back. Let's say I integrated t to the 4th. I got t to the 5th over 5 plus c, plus integrate 2, be 2x, or 2t, excuse me, plus some other c. I'm going to call it c2, just a different constant. Well, if I add these two together, if I add a constant and a constant, it just equals a constant. So whenever that happens, if you have separate integrals like that, I don't have to put 2 different constants. It's going to be, when I add those together, it's just going to be a constant anyway. All right, let's try. Let's actually have you try. You guys try number 7. So pause the video. Try number 7. 8 and 9 are a little bit different. They're a little bit trickier. We've got to do some work beforehand. But try 7. See, and pause it, try it, come back. I'll go through it with you, and then we'll do 8 and 9 together. So number 7, again, you can do each piece separately. I don't care if you rewrite it separately. You can do it all at once if you want. So if I integrate 2y squared, I'm going to go 2y, I add 1 to the power and divide by the power. 4y, again, I add 1 to the power, so it'd be 4y squared and divide by the power. And the 1's a constant, so when I integrate it, it would just be 1y. Let's do a little bit of simplifying. So I get 2/3 y to the 3rd. 4 divided by 2 is 2. And there's my integral. If you ever want to check, right, we could take the derivative. If I take the derivative, the 3 would drop down. 3 times 2/3 is 2. 2y squared. The 2 drops down, be 4y. Derivative of y would be 1. Okay, 8 and 9 are a little bit trickier. This should, hopefully we can think back to when we did derivatives. When we did derivatives, we always try to simplify the expression to make it just be x to a power. We do the same thing here. If I can rewrite this as just being x to a power, it'll make it a little bit simpler to work with. So let's try that first one. So what I'm going to do is first rewrite it as being the integral of 3x to the negative 2 minus, and then I have 1, and the square root of x, I can make it x to the 1/2 and move it up to the top and become x to the negative 1/2 power. So what I'm trying to write it as just being something times x to a power, plus or minus something times x to a power, because now I can just apply that power rule for integrals. Okay, so let's integrate. So this comes out to be 3x, add 1 to the power, it'd be -1, and divide by that new power. Same thing here, add 1 to the power, so it would be x to the 1/2 divided by 1/2. Then let's just do a little bit of simplifying. The 3 divided by -1 would be -3. I'm going to move the x back down to the bottom. And then dividing by 1/2 is the same thing as timesing by 2. And that's really as far, there's nothing really left to simplify after that. All right, number 9. So again, I want to write it as just being x to a power. So one strategy is when your denominator is a monomial, if you remember, we simplified that by splitting it apart into separate fractions. So I'm going to split it apart. I'm going to write it as being square root of x over x squared plus 1 over x squared. I'm going to erase this over here just so I have a little bit extra room. And now I want this just to be x to a power, so I want to combine those x's together. So I'm going to first think about that square root of x up on top. I'm just going to rewrite it as being x to the 1/2. Okay, remember our rules. If I have two bases that are the same, I can keep the base the same and subtract the exponent. So I go 1/2 minus 2. That's a -1.5 or -3/2. And then the x to the 1 over x squared I'm going to write as being x to the -2. So I've got to do a little bit of work first, a little bit of, use some algebra to do some manipulations, but I want to end up just being x to a power plus or minus x to a power. Okay, now let's integrate. I'm going to come up over here. So x to the -3/2, I'm going to add 1, so that'd be x to the -1/2 divided by -1/2 plus x, add 1 to the -2 would be -1 divided by -1 plus c. Let's do a little bit of simplifying. Dividing by -1/2 is the same as timesing by a -2 minus x to the -1 plus c. Let me erase that. Okay, now they've got negative exponents, so I'm going to move them to the bottom. Okay, that should be my integral right there. So it can get a little bit trickier, especially, you got to do you can end up with some fractions. But the big thing here is this step right here, going from there down to there, is making sure you use what we know about algebra to try to manipulate it and change it into a form where I just have x to a power plus or minus x to a power. Because you can't use the power rule until that happens. You always got to have that plus c when you integrate. When we take a derivative, you don't, right? Because the derivative of a constant is 0, so it goes away. But when you integrate, you have to add that constant on. Sometimes they'll give you an initial condition that makes it possible to actually find out what c is. So here's an example. I know f prime of x equals x to the -3. It tells me f of 1 equals 3/2, and it wants me to find f of x. In other words, it wants me to integrate this. So let's do that. F of x would equal, I'm going to add 1 to the power, x to the -2 divided by that new power plus c. Just do a little bit of simplifying. So that would be a -1 over 2x squared plus c. Now normally we'd be done there because I don't know what c is, but right here it gives me what we call an initial condition. It tells me when x is 1, the function equals 3/2. So I can plug that in and figure out what c is. So I'm going to say when I plug 1 in, I get 3/2. So 3/2 equals -1 over, I just need to work that out. So 3/2 equals a -1/2. I add the 1/2 over, that's 1.5 plus 1/2, so it ends up being, what, 2? So c is equal to 2. So my final thing, my function, f of x is equal to -1 over 2x squared plus 2. Okay, so there's my answer right there. So when you're given an initial condition like this, you need to find out what c is equal to. Otherwise, you don't worry about it. You're just going to tack a plus c on the end there and be done. But if you do have that initial condition, you can actually solve for c and find out what c is equal to. So here's one. Think about this for a second. It says, what is the derivative of the integral of 5 squared of x minus 1x squared. So just think about what would happen here. If I want to take the derivative of an integral, hopefully you're thinking, inverses, inverse functions. They're going to cancel each other out. Just to show you that it does, you don't need to write this down or work through it, but I just want to show you really fast. If I start just with this and I take the integral of that, so I'm going to do the integral of 5x to the 1/2 minus, I'm just going to write it that way. Well, so let's integrate that. That would be 5x to the 3/2 divided by 3/2. Dividing by 3/2 is the same as timesing by 2/3. Oops, sorry, 2/3. Let's do this also. So minus x to the -1 divided by -1. Okay, so that ends up being 10/3 x to the 3/2 minus or plus 1 over x or x to the -1. And now, that's what this part came out to be. Now it wants me to take the derivative of that. Well, if I take the derivative, the 3/2 drops down. 3/2 times 10/3 is just 5. Then subtract 1 from the power. Plus, x to the -1, the -1 drops down. Subtract 1 from the power. And when we get all done here, this ends up being just what's on the inside, which should make sense, right? If I integrate a function and then I take the derivative, those are just inverse operations. They're working in opposite directions. So that's my answer. Oh, by the way, I'm sorry, I forgot. This answer should have had a plus c on the end. But when I take the derivative, right, the plus c is going to go away. So it's gone. So derivative and integral, just know that they're inverses. They're going to cancel or undo each other. Okay, the last thing we're going to talk about here is, right, we've done a lot of physics. And what we talked about is if you have the position function, you can take the derivative to find the velocity, and you can take the derivative of the velocity to find the acceleration, right? So I take the derivative, it takes me to from position to velocity, or from velocity to acceleration. Well, now I can work backwards. So if I integrate, I can go backwards. If I have the acceleration function, I can work backwards to find the velocity. Or if I have the velocity, I can work backwards to find the position. So now we can go the opposite direction. So you'll have a little bit of this on this assignment. So it says down here, the example 12, the acceleration of a particle at time t is given by, and there's my acceleration function. And then it gives me some initial conditions. It tells me v of 1 equals 6 and s of 2 equals 5. And now it wants me to work backwards to find the velocity equation and the position equation. What that means is I'm going to integrate. So to find the velocity, we know the velocity is the integral or the antiderivative of the acceleration. So I'm going to take the acceleration function, which is 4t minus 3, and I'm going to integrate that, and that should give me what the velocity function is. So let's do that. So if I'm going to integrate here, the velocity function equals 4, add 1 to the power, 4t squared divided by 2 minus 3t plus c. We can do a little simplifying there. 4 divided by 2 is 2, so 2t squared minus 3t plus c. That's what my velocity function equals. Now, right now I just have that plus c there. It gives me this initial condition up here. It tells me v of 1 equals 6. I can plug 1 in for t then, and the velocity has to equal 6, and that will allow me to find out what c is equal to. So if I plug 1 in, I get 6, plugging 1 in for t. Let's figure out what c is equal to. So that would be 2 times 1 squared is 2, minus 3, plus c. So I could minus the 2 over and add the 3 over. You end up with 7. So if I come back up here, my velocity function, I'm going to put it up here, is equal to 2t squared minus 3t plus 7. I find out what c is equal to. So because of that initial condition, like we just talked about, I can actually solve for c. Okay, now we're going to find the position function. Well, to find the position function, right, the position function is the integral of the velocity function. So it's the integral of 2t squared minus 3t plus 7. Okay, so let's integrate that. So let's see, I end up with, what, 2t cubed divided by 3 minus 3t squared divided by 2 plus 7t plus c. Now, if I didn't have an initial condition, I'd be done there. But up here, it tells me s of 2 equals 5. That means I can find out what c is equal to and get my position function. So I know when I plug 2 in for t, I get 5 out for the position. So 5 equals 2 times, you'll see 2 cubed would be 8, times 2 would be 16, minus 3 times 2 squared. 2 squared is 4, times 3 is 12. Plug 2 in there. 7 times 2 is 14. Okay, let's solve for c and find out what c is equal to. So let's see, 12 divided by 2 is 6, so minus 6 plus that, so it'd be 5 equals 16 thirds, minus 6 plus 14 is 8, I believe. So we could minus the 8 over is negative 3, minus the 16 thirds over. Okay, that's what c is equal to, and you could work that out and find it out, or you can just plug that in right up here. You can leave it like that. So my final thing, my position function is 2 thirds t cubed minus 3 halves t squared plus 7t minus 3 minus 16 thirds. And again, we could definitely combine those together. I'm just being lazy and not doing the fractions. So physics, so we can do a bunch of physics stuff with that. Hey, just last thing, kind of cool is if you talk about if you have an object that's like falling towards the earth, falling downward, the acceleration is constant because of gravity, and the pull of gravity, or the acceleration is approximately negative 32 feet per square second. Well, what we can do then is we can actually work backwards to come up with a formula for the position function of any object that is falling towards Earth that has that same pull of gravity. So let's do that really quick. I know my acceleration is constant. It's always negative 32. So to find the velocity, I have to integrate the acceleration. Well, it's just a negative 32. I guess I don't really need the parentheses there, but that's okay. So if I integrate a constant, that means the velocity is going to be negative 32t, just add a variable on the end there, right, plus c. Up here it says v of 0 is the initial velocity. So just think for a second. When the velocity is 0, that part's going to come out to be 0. So when I plug 0 in for t, really the velocity is going to equal this number over here. So I'm just going to rewrite it this way. V of t equals negative 32t plus the initial velocity plus v0. So this constant really over here really is the initial velocity. Okay, now let's integrate that to find the position function. So I need to integrate that. I'm going to integrate negative 32t plus v0. Okay, so when I integrate that, I end up with, I'm going to add 1 to the power plus c. Let's do a little bit of simplifying. So s of t is equal to negative 16t squared plus the initial velocity times the time plus c. Now, up here it tells us we're going to s of 0 equals the initial position. Just think about this for a second. The initial position is the position at time 0. If I plug 0 in, this term comes out to be 0, and this term comes out to be 0. That means this constant really is the initial position. So I'm just going to rename it. I'm going to say my position function is negative 16t squared plus v0t plus s0. So this really is a formula. If you have any object, if you know the initial velocity and the initial position, you can plug those two things in and you end up with a formula, you end up with a position function that would tell you the position of the object at any given time. So anyway, that's kind of a cool thing. Just using calculus and integration, you can work backwards and come up with that formula. And this is one that's used quite a bit in physics that you run into a lot. So, all right, so I think that's it for this chapter, or for this, not the chapter, we wish, right? For this first section for 6.1. Let me know if you have questions. Good luck.